Section: Introduction. In this section, we discuss model merging, which is a recent advancement in the large language model (LLM) field that has brought about a significant change in approach. Model merging involves combining multiple LLMs strategically to create a single architecture. This method has gained attention from researchers because it offers a key benefit: it does not require additional training, making it a cost-effective way to develop new models. This accessibility has sparked a surge of interest and experimentation in model merging. Merged models now dominate the Open LLM leaderboard, demonstrating the potential of this approach in democratizing foundation model development. However, many consider model merging to be a complex process, often likened to a black art or alchemy. It relies heavily on the intuition and instincts of the model maker when selecting and merging models to create a new model that performs well for a specific task. Additionally, the model maker typically needs domain knowledge across various benchmark tasks. With the wide variety of open models and benchmarks available, relying solely on human intuition has its limitations. We believe that a more systematic approach, such as using evolutionary algorithms, can lead to the discovery of more effective model combinations, automating the creation of more capable models. In our work, we demonstrate how evolution can be utilized to uncover innovative ways to merge different models, resulting in new models with enhanced capabilities. We introduce a methodology that leverages evolutionary algorithms to facilitate the merging of foundation models. Our approach is unique in that it navigates both the parameter space, weights, and the data flow space, inference path, integrating these dimensions into a cohesive framework. Our work makes several significant contributions to the field of foundation model development. We introduce evolutionary model merge, a general evolutionary method that automatically discovers optimal combinations of diverse open-source models to create new foundation models with specific capabilities. This approach taps into the collective intelligence of existing open models, enabling the creation of powerful models without the need for extensive training data or computational resources. We also demonstrate that our method can merge models from different domains, surpassing the capabilities achievable through traditional human design strategies. By automatically generating a Japanese LLM with math reasoning capability and a Japanese vision language model, VLM, we showcase the effectiveness of our approach. These models achieve state-of-the-art performance on various benchmarks, highlighting the efficiency and generalization capability of our method. Furthermore, our work challenges the conventional paradigm of expensive model development by showing that our evolutionary-based method can produce competitive models without relying on gradient-based training. By open-sourcing our state-of-the-art Japanese foundation models, Evo LLMJP and Evo VLMJP, we aim to foster further research and development in the field. This paves the way for exploring alternative, more efficient approaches to foundation model development. Section Summary. In this section, we introduce model merging as a groundbreaking technique in the large language model (LLM) community, where multiple LLMs are strategically combined into a single architecture without additional training, revolutionizing model development. By leveraging evolutionary algorithms, we propose a systematic approach to automatically discover optimal model combinations, showcasing the creation of high-performing Japanese LLMs and vision language models, VLMs, that outperform previous models. Our method challenges traditional expensive model development paradigms by demonstrating the efficiency and generalizability of evolutionary-based model merging, paving the way for more cost-effective and versatile foundation model development. Section: Merging language models. In this section, we explore merging language models using various methods. We found that simple weight interpolation, which works well for image generation models, can also be used for language models under certain conditions, but it may lead to performance issues. To address these issues, new methods like task arithmetic and ties merging have been introduced. Task arithmetic involves manipulating task vectors by adjusting model weights, while ties merging focuses on resolving parameter interference to improve merging performance. Another method called DARE zeroes out small differences between models and amplifies larger differences to enhance merging. These methods, especially DARE, are often used in combination with task arithmetic or ties merging. The implementation of these merging techniques in open-source toolkits has significantly boosted the merging of image generation and language models in the community. MergeKit, a popular toolkit, offers various merging recipes such as linear interpolation, task arithmetic, ties merging, and DARE. Users can experiment with combining these methods to create merged models based on fine-tuned base models like Mistral. Additionally, MergeKit introduces frankenmerging, a method that allows users to stack layers from different models to create new architectures, offering flexibility beyond traditional weight merging methods. While frankenmerging presents exciting possibilities, discovering new techniques remains a challenge that requires more experimentation. The field of model merging is still underexplored, and we believe evolutionary algorithms can play a crucial role in advancing merging solutions. By leveraging evolutionary techniques inspired by natural selection, we aim to discover novel and effective merging strategies that traditional methods may overlook. Our approach aligns with the concept of neural architecture search (NAS) in deep learning, where evolutionary algorithms are used to explore new architectures efficiently. Unlike NAS, our method focuses on optimizing model merging recipes and layer stacking without the need for extensive training, utilizing existing transformer blocks as building components. This approach allows us to explore a wider range of model combinations and potentially create entirely new neural architectures. Section Summary. In this section, we explore the challenges and advancements in merging language models, highlighting the limitations of weight interpolation-based methods due to parameter interference. We introduce innovative techniques like task arithmetic, ties merging, and DARE to address these issues and improve merging performance. Additionally, we discuss the potential of evolutionary algorithms in optimizing model merging recipes and layer stacking, offering a systematic approach to discovering novel and effective combinations beyond human intuition. Section Method. In this section, we aim to develop a comprehensive framework that can automatically create a combined model from a set of base models, ensuring that the performance of this combined model is better than any individual model in the group. Our approach heavily relies on evolutionary algorithms to fine-tune the complexities involved in merging models. To tackle this challenge systematically, we break down the merging process into two separate configuration spaces and examine their effects. We then introduce a unified framework that seamlessly brings together these spaces. A diagram illustrating our approach is shown in the figure. When merging models in the parameter space, PS, our goal is to blend the weights of multiple base models into a single entity with the same neural network structure, but with improved performance compared to the individual models. While there are various methods for combining model parameters, we use task vectors analysis to understand the strengths of each model based on the tasks they excel in. We enhance ties merging with DARE to allow for more detailed merging at the layer level. We define merging configuration parameters for sparsity and weight mixing at each layer, including input and output embeddings. These configurations are optimized using an evolutionary algorithm like CMAS for specific tasks, guided by important task-specific metrics such as accuracy for MGSM and Rouge score for VQA. In contrast, when merging models in the data flow space, DFS, we focus on optimizing the path that tokens take as they move through the neural network, without altering the original weights of each layer. For instance, a token from Model A at the ITH layer may be directed to the JTH layer in Model B. Initially, we limit ourselves to simple serial connections and non-adaptive setups in this domain, leaving more flexible model merging for future exploration. Our method searches for a sequence of layer indices that define the path tokens should follow for a specific task, considering a collection of n models and a budget T. The search space can be quite large, but we reduce it by introducing an indicator array that manages the inclusion or exclusion of layers based on repetitions. This adjustment makes the search space more manageable for evolutionary search algorithms. We focus on optimizing the data inference path within the merged model while keeping the parameters in the individual models unchanged. In our experiments, we observed that rearranging layers, especially repetitive or permuted sequences from earlier in the model, can negatively impact performance. To address this, we include an indicator array in the evolutionary search space to control the inclusion/exclusion of layers. Additionally, we optimize a matrix W along with the indicator array to scale inputs appropriately, which helps mitigate issues arising from distribution shifts. The size of W grows quadratically with the number of layers, but we can also explore parameterizing W with a neural network to contain the search space size. Section Summary. In this section, we aim to develop a comprehensive framework that automatically generates a merged model from a set of foundational models, surpassing the performance of any individual model. Our approach involves utilizing evolutionary algorithms to refine the merging process, dissecting it into parameter space and data flow space for analysis and optimization. By enhancing merging configurations with techniques like task vectors analysis and layer-wise merging, we strive to create a unified model that optimizes both model parameters and data flow paths for improved performance on specific tasks. Section: Merging in both spaces. In this section, we explore merging models in both the parameter space, PS, and the data space, DFS. These two merging approaches are different but can be combined to enhance the performance of a merged model. By first applying PS merging to a group of models and then incorporating this merged model back into the group for DFS merging, we can improve the final model's performance significantly. This combined approach is particularly useful for model merging with multiple objectives. Initially, PS merging can create several merged models, each focusing on a specific objective. Subsequently, DFS merging, using multi-objective genetic algorithms like NSGA2, can further enhance the overall performance of the final model across various metrics. Our goal is to go beyond the typical task optimization seen in existing merged models and instead explore merging models from diverse domains, such as non-English language and math, or non-English language and vision. This approach allows us to create models with broader real-world applications and move beyond the limitations of models optimized for specific tasks defined by leaderboards. To demonstrate our evolutionary model merge method, we evolved a Japanese language model, LLM, capable of math reasoning, and a Japanese vision language model, VLM, proficient in handling culturally specific content. By merging a Japanese LLM with an English math LLM, we developed a Japanese math LLM, and by merging a Japanese LLM with an English VLM, we created a Japanese VLM. To achieve this, we applied evolutionary model merging to a set of source models containing a Japanese LLM and math LLMs, namely Shisa Gamma 7BV1, Japanese LLM, Wizard Math 7BV 1.1, and Able 7B002, all fine-tuned from Mistral 7BV 0.1. For testing, we utilized the MGSM dataset, a multilingual translation of a subset of the GSM-8K dataset. The Japanese test set from MGSM, comprising 250 samples, was used for the final evaluation. To prevent overfitting, we translated the remaining 1069 samples from the GSM-8K test set into Japanese for the evolutionary search. In our evaluation, we focused on generating Japanese answers to math problems. We considered an answer correct if the final numerical value was accurate, and the reasoning text was in Japanese. To handle variations in output formats due to merging models trained differently, we adopted a heuristic approach that proved effective in extracting correct answers in most cases. For optimization in PS, we employed the CMAS algorithm with default hyperparameters in Optuna. The fitness value was based on the accuracy across all 1069 training samples. The best trial after 1000 iterations was selected as the final model. In DFS merging, we used ties merging with DARE and optimized parameters for M equals 64 and R equals 3, resulting in T equals 192. We limited the merging to two models, A and B, to ensure the final model size remains manageable for a single GPU. Throughout the merging process, we utilized Model A's tokenizer and input-output embeddings. We set up the indicator array to prioritize Model A's layers in the inference path, shortening the search time. The performance was evaluated based on the validation set, with the test set kept separate from the optimization process. Section Summary. In this section, we explore the combination of model merging in the parameter space, PS, and in the decision function space, DFS, to enhance model performance. By sequentially applying PS merging followed by DFS merging using multi-objective genetic algorithms like NSGA2, we can effectively merge models targeting different objectives. Our evolutionary model merge approach demonstrates the potential to merge models from diverse domains, such as merging a Japanese LLM with an English math LLM to create a Japanese math LLM, leading to models with broader real-world applications. Section: Results. In this section, we present the results of our study on the performance of language and math models, LLMs, on Japanese math and overall Japanese tasks. The table summarizes how different models performed on these tasks. We observed that while the Japanese language model, Model 1, struggled with math, the math models, Models 2 and 3, had difficulty with the Japanese language. As a result, all three models scored poorly on the tests, with accuracy levels around or below 30.0. However, when we combined these models, Models 4 to 6, we saw a significant improvement in performance. The model that merged in PS, Model 4, achieved an impressive score of 52.0, showing the potential of combining models with different expertise. The DFS merged model, Model 5, also showed improvement, with over a 6% increase in accuracy compared to the source models. Our hybrid model, Model 6, which integrated both merging strategies, showed further enhancements in performance. The models we merged retained the foundational knowledge from the source models, as seen in their similar score patterns on certain problems. They also showed new capabilities by successfully solving problems that the source models struggled with. By effectively combining a Japanese LLM with mathematical models, we created models proficient in both Japanese language understanding and mathematical problem solving. Additionally, we evaluated the general Japanese language ability using the Japanese Language Model Evaluation Harness, JPLMEH, benchmark suite. Our models achieved high scores, surpassing both the source models and even the previous state-of-the-art Japanese LLM with more parameters. Notably, there were improvements in various tasks such as JS-Quad and JAQKET. In our exploration of model merging, we experimented with different configurations but found that simpler settings, like the PS merged model, Model 4, yielded the best results. The evolutionary merging process highlighted the importance of all three models, with the Japanese LLM playing a critical role. By incorporating the phosphorus monosulfide merged model and applying DFS merging, we achieved optimal performance. The evolution of the inference path showed the significance of certain scaling parameters in the model's effectiveness. Section Summary. In this section, we present the performance evaluation of various language and math models on Japanese tasks. Our merged models, combining expertise from different models, show significant performance improvements, with some achieving scores as high as 52.0, demonstrating the effectiveness of integrating Japanese language understanding and mathematical problem-solving capabilities. Additionally, our models outperform previous state-of-the-art models in Japanese language proficiency tasks, showcasing the success of our evolutionary model merging approach in enhancing overall model performance. Section: Multimodality Extension. In this section, we extend our method to multimodal models and create a culturally specific content-aware Japanese VLM. VLMs have made significant progress recently by utilizing pre-trained LLMs for text generation. A VLM typically consists of a vision encoder, an LLM for text generation, and a projection network to map image features into the LLM space. The LLM is initialized with pre-trained models for text generation. During training, the projection network and sometimes the LLM are trained on various vision language datasets, while the vision encoder remains fixed. The LLM component in a VLM can be seen as a standalone LLM with the added ability to understand visual prompts. By focusing on the LLM component and merging a Japanese LLM with a VLM, we aim to enhance the LLM's capabilities. We use specific models for this experiment: Shisa Gamma 7B V1 as the Japanese LLM and LLAVA 1.6 Mistral 7B as the VLM. Creating a Japanese VLM benchmark was necessary due to the limited availability of public Japanese VLM datasets. We evaluated our VLM on a Japanese VQA dataset, which includes a test set extracted from the Japanese Visual Genome VQA dataset and a set of images and questions related to Japanese culture. In our experiments, we compared our VLM with two baselines, LLAVA 1.6 Mistral 7B and a Japanese stable VLM trained from scratch on Japanese datasets. We used Rouge L to evaluate the models, focusing on Japanese responses. We applied the same optimization settings as in our previous experiments to merge the source models in the parameter space. Our VLM outperformed the baselines on the benchmarks, showcasing its proficiency in Japanese and cultural content understanding. Our method leverages evolutionary techniques to combine different models effectively, creating new foundation models with desired capabilities. By merging models from diverse domains, we can achieve state-of-the-art results on various benchmarks. This approach shows promise for developing high-performance models through evolutionary model merging. Section Summary. In this section, we extend our method to multimodal models by evolving a culturally specific content-aware Japanese VLM, which combines a Japanese LLM with the LLM component of a VLM. The VLM architecture includes a vision encoder, an LLM for text generation, and a projection network, with the LLM component initialized with pre-trained LLMs. Our VLM shows enhanced performance on Japanese benchmarks, demonstrating successful evolutionary merging of different models to navigate culturally specific content effectively. Section: Limitations. In this section, we recognize that our evolutionary model merging approach combines various expertise from different models, but it also inherits their limitations. We observed cases where the merged models generated responses that were not logically coherent. Moreover, our study does not cover fine-tuning or aligning instructions, which could lead to the models producing outputs that are factually incorrect. Regarding author contributions, Takuya Akiba initiated the project, developed the project design, and started the experiments on merging models in parameter space, laying the foundation for the methodology. Makoto Shing expanded the merging of models in parameter space to include vision language and diffusion models. Yujin Tang led the work on merging models in data flow space by incorporating ideas from neural architecture search and morphology evolution literature, establishing key methods in this area and in hybrid merging strategies. Chi Sun helped implement our framework for merging models in parameter space and supported in evaluating the models. David Ha provided overall guidance for the research project, giving technical insights, advice, feedback, and writing assistance.